Damen und Herren, ich gebe euch der Knut Janke. Er ist Astrophysiker, interessiert sich in Galaxien, schwarzen Löcher sowie Urbanismus und
So, dann fangen wir mal an. Welcome to the English translation, and Knut Janke will tell us about Euclid, the new space telescope. And here we go. Knut, please. Thank you very much. I'm happy that I have the opportunity to talk about Euclid, and I'm very excited because it's really very new, the whole thing, and I've come full circle really because 40 years ago in Hamburg there was my first contact with astronomy in the planetarium and first contact with black holes, and this is my research area now, just 400 meters away. I studied physics a long time ago, and I passed my old school way here, and it's about Euclid, the new space telescope of the ESA, a cosmology mission that is now in space. And I work on the Max Planck Institute in Heidelberg, and I speak for the consortium and the people who have built this thing and who do the research. And we really had not time enough to build 3D models, but I talked about cosmology, and I have to do a little introduction. Why is it interesting? What we are doing there? What's dark matter, what's dark energy, and how can we see things that are dark? How are we doing that? So an introduction to Euclid, how does that work? What does the telescope look like? What kinds of instruments are there and what diagnostics? And beautiful pictures in the end, and links where you can zoom in and out in these wonderful, beautiful pictures, and you will see dark matter, dark energy. The universe on one slide, 13.8 billion years since the Big Bang. The x-axis is the time, the y-axis is the size, about the scale in the universe. Everything was very compact and hot in the beginning, and that is called the Big Bang, and it has been expanding ever since. And there was a phase where it was very, very fast, in fractions of a second, became very large. And with the expansion came a cooling, temperatures were going down, and eventually it was cold enough so that hydrogen nuclei and electrons combined, and it became transparent to light. And that meant that this time is the time that we can see, that's the first thing that we can see, and it's about 2.7 Kelvin microwave background radiation. That's what that is. And after that, time and stars formed, and galaxies formed, and planets, and in the end, it's 13.8 billion years after the Big Bang. And if we look back, we can diagnose how it was at that time, how it was with this microwave background. That's one point, and that's what Planck did in the ESA mission. And we learned very interesting things, three important things. We know about the geometry of the universe, in geometry in 3 dimensions, and it's about curvature of space. And it's if we really have lots of mass, high mass density, then if we looked at it in 2 dimensions, it would like a ball, like a sphere with positive curvature. And if it was very little mass, it could be like a saddle shape. And if there was very low energy density, then it would be very flat. And Planck has measured and looked, and there is really no curvature. And that means we can infer from that the energy density in the universe that has to be there in the universe at this moment, and the so-called critical mass that makes the universe flat. The whole total energy density in the universe is something we know now, and that's a lot to know, actually. So, who has looked very precisely near the now time? There's the edge that shows the edge, and that's curved to up and down in the end. And what does that mean? We should expect, if we have mass and density and gravity, that it should decelerate the expansion, and if it should slow down really, but it doesn't. And that this revelation is 20 years old, and we have something that accelerates the expansion of the universe. And this is very interesting because now we only know about matter, and if there is something that pushes apart, that has to create another pressure, and that isn't what gravity does. And we have something that accelerates the expansion, and we have something that is somehow energy and makes pressure, and we don't know what it is. We call it dark energy. So we have a name for that. That's good. The third part, if we take a galaxy and look how it rotates, spiral galaxies are rotating, and our Milky Way does as well. And if we look the rotational speed versus the radius, if we know the radius, then we know how much mass there is inside of it, and we can calculate. We take, for example, the Andromeda galaxy, and we calculate what the amount of light that we have. We know the number of stars and so on, and then we look how much mass there is, and we calculate from the velocities and the mass, and it just doesn't fit, and it doesn't fit at all. In the inside, it's sort of okay, but there is mass missing, and it's not bright, we can't see it, and we give it a name. So there's mass, it doesn't shine, so it is dark matter, and that's all right. And now we can calculate, we have information, we can among other things, we can how much of it should be here in this hall, and the dark matter should be around 5 femtograms, 5 times 10 to the minus 15 grams in this hall. Whatever it is, we don't know what it is, and it's not a lot. And dark energy is about 10 to the minus 18 grams. And obviously that is a lot more than we have at normal matter. And that shows us something. We are not at a normal place in the universe, but we are in a hall, in a planet, in a solar system, in a galaxy. It's not the average of the universe. And if we now look exactly what we have in total energy density in the universe from the cosmic microwave background, and this is normal matter, that's roughly on average just 5%. Everything that we see, what we see in the sky as amateur astronomer or as professional astronomer with the best telescopes, is 5% of the total matter, 5 times as much as dark matter, and the rest is dark energy. So if we calculate, we don't know what dark energy is, we don't know what dark matter is, but that's 95% of the energy density in the universe. And that's not really satisfying, let's say. We know what it is not, but we have lots of theories, what kinds of particles those are. The accelerators, the physicists looked in the accelerators and didn't find anything that could be dark matter. Dark energy, there's even more what kinds of fields this could be, how it connects to the inflationary expansion of the universe. But between that, we can't decide, we can't really exclude any theories. A lot was done from Earth. Whatever we could do from Earth is going on, but that's not enough, and so we have to go into space, and I hope it becomes clear why that is necessary.
We need a special cosmology mission. The diagnostics that I'll explain in a minute to define these dark energies. What's that? Euclid is the mission of the European Space Agency inside the Cosmic Vision 2015 to 2025 thing. It's a middle-class mission, which means it's about $1 billion. Like 1.4 together with the Russians. We want to define dark energy, we want to measure dark matter, we want to know more about gravitational law. Maybe there has to be some adjustments, everything around that. What we have are 2 main methods. One is the weak gravitational lens effect, to show the dark matter structure of the universe, and the other is the baryon acoustic oscillations, which is like the expansion history of the universe. I'll explain shortly. The gravitational lens effect, maybe you heard it, maybe not. Lenses break light. So if you take a special sort of lens, light is shown somewhere else. So you might get 2 images instead of 1. So you get two images of a falling beam. So if you have matter, it curves the space. If space is curved, light might go around the edge. That happens if you have a source like a galaxy, and in between there is a large amount of mass, and it looks like I have two images, one to the left and one to the right. That's the gravitational lens effect, the strong gravitational lens effect, and you can see that in nature. Nature means you take a space telescope like Hubble, and everything you see here, which is very bright, except for this star, this cross star. These are all galaxies. I'll try using my mouse. These big, bright things are galaxies, and these galaxies of the galaxy cluster, these weird elongated structures in here, these galaxies are all the same. We have multiple images of the same galaxy. The images get stretched, and if it's correct, we get these arcs. This is the strong gravitational lens effect. We've known about that for a long time. That is just a matter of gravity. We use the weak version of that, so not the main diagnostics to get multiple images, but we use that light going through space, moves along masses and gets distracted a little. And if we do measure that in a big amount, we can actually look into the backlighting of it. And as we can see here, they're all elongated systematically and go around certain areas. These white lines are the main axes of elongated galaxies. And if we do that, we can see, okay, there's like a big amount of mass. And this is a function of distance with galaxies far away and not as far away and so on. Group them differently. We can have a three-dimensional map. The three-dimensional map of mass in space. There's bright and dark matter, and dark matter dominates, and we get a three-dimensional structure distribution of matter in the universe. And like far distances and times back. The second thing is baryon acoustic oscillation. The microwave background radiation is from a time like 300 years after the Big Bang. That's very, very far back. And what we see there is very small differences in temperature, which stem from a difference of density of matter. And a different density and gravity, if there's like over density, there's more matter is accumulating, and when there's more goes away. And if this keeps happening, you have like these knots of filaments where basically all the galaxies accumulate together. So we have information of this very early time and this much later time with gravitation and structure and so on. And there's one length in this microwave background radiation. This has to do with the horizon and sonic waves and so on, and this measure is in these tiny these differences of density back then, and this is a measure of density of galaxies. So this measure stays because the over density doesn't lengthen a lot. So if you look at this as a function of time, you will see the following. If you take a galaxy and measure how many galaxies are there in distance of 1 light year, 100 light years, 10,000 light years, and so on. If you're in the Milky Way, there's a lot of galaxies. We are in the local group. There's Andromeda and other smaller galaxies. If you go further out, there's like the mean, the average of the universe. And it's mostly so instead, but not there. There's a small overdensity. That's the same overdensity that we already had. This is the measure, and this measure is expanding with the universe. And the problem we have with the cosmology is that we can't touch. And this distance is expanding, and we can measure it for different amounts of billions of years ago. And the question is, what power does that? Can we see how exactly this expansion history went, and what will happen with the powers, with the forces we have? And well, we do that with this length and do it as a function of time, and then we can measure it in a way. So we have to look at different forms of galaxies and the positions of galaxies. What we do, we take the weak gravitational lens effect, we look at a distance in form of 2 billion galaxies. That's not a small amount. For the baryon acoustic oscillation, we need the exact 3D position for 35 million galaxies. So we have to look at a lot of the sky and go back a far amount of time. It's like a third of the whole sky. We need images, spectral images of light, and that is what Euclid will do. Yes. So what do we have? We have a satellite telescope.
So 1.2 meter mirror telescope, that's what it looked like in the test phase. We have a main mirror that collects light for 1.2 meters. It's about half of what Hubble has, so it's about half of the resolution, but that's enough for us. And we have two instruments, one in near infrared and one in visible light. And with that we can cover near infrared for distances and for visible lights for very, very precise measurement of the forms of galaxies, the shapes of galaxies. So what is different with this telescope compared to Hubble or JWST, which just launched? And that's the field of view. And Hubble and JWST can look very, very precisely, very small areas, and it's very important for a lot of research. But if you look at the moon in comparison, if you want to scan the moon, which you can't really do, it's far too bright, it's far too close, but you would need a lot of time. But we really want to scan 1/3 of the sky. We could use Hubble or JWST, but it would really take 500 years, and you don't get the money for that. So what's different? The telescope is designed from the base up to look at big areas of the sky, and that's what Euclid does. We have an area that's 2.5 times the size of the moon, and we can very quickly scan the entire sky. That means a few years, but not a few hundred years. And that means a completely different architecture, a completely different design of the optics. So the instruments, it's the near-infrared instrument. It's really about a meter in size, and I worked on that as well, and we did that. What does it? It's in the name, it's near-infrared spectroscopy, and we split the light up into the wavelengths and do direct distance measurements, and we can also make pictures for measurements in the... It's a bit redder than the visible light, and the other is really how we measure the exact and precise and very stable shapes of galaxies. And this is really about this size. It's 36 CCD sensors with a lot of pictures. This is a full-frame camera. If someone, it's a very expensive camera, and the optics for that isn't really not. You can't carry that anymore. But what we want to do is really measure shapes. So what is this about? The Earth is round, the Moon is round, so we know that. Not exact, not exactly the same. The Moon has an eccentricity of about 0.00125, and the Earth of about 0.0335. It's because of the history of their creation, and this really has to differentiate between that, and we really have to be able to measure the difference. But with pictures like this, or only half of the pixels of these. And to do that precisely and accurately is really the difficulty, because we need a camera that is extremely stable and really, by its design, need to be calibrated and very, very stable, and really need to know all the instrument effects. And that's why Euclid is where it is, in a very stable orbit, thermally stable orbit, and a big part of the problems was this kinds of measurements. And so we have NISP and VIS, and the golden is the 1 meter NISP, the near-infrared, and the black box is the visible instrument. There are no lenses, there are some mirrors that focus and have a wavelength bandpass, as little as possible in between, as simple as possible. And if you put that together, then it's still quite big now. This is about the instrument area, and above that is the telescope. And we have really quite a big size. It's not really a CubeSat with 5 centimeters, as we heard before, but it's a bigger variant. So who is building that? It's an ESA mission. So Euclid is a cooperation between ESA and a consortium from, I think, about 3,000 people by now, 15 countries, 150 institutions, universities, lots of industry partners. And the consortium where I work has really designed the instruments and built them and financed it and makes the scientific data processing and in the end the scientific results. And the ESA had the framework and paid for the telescope. And so what's behind this? Let's take a look at that. So this afternoon there were development cycles of 6 months. So the precursor concepts were from after we found that there must be dark energy around the 2000, and between 2005 and 6, 7, there were a few concepts, papers were written, and then we have 2 possible diagnostics. We want to do that in 1 mission. There was the original concept of Euclid in 2009, 2011, and Euclid was selected by ESA as the mission. NASA is the junior partner, and since then we have been building 6 or 7 years of instrument development, then tests, delivery to the ESA, and built it into the telescope, more tests and even more tests. And then this year, finally, everything that went pretty quickly. 2 years ago, we didn't even have a rocket, and then it was quite fast. I really can't understand. It was 10.5 months away. I was in Cannes with colleagues, and we could look at the final finished monster, and it was in February this year. And 6 weeks later, it was packaged and went onto a ship, and 2 weeks later, it arrived in Florida, was unpacked. Another 6 weeks later, it was fueled. There's a launch adapter now attached, and then in the 1st of July this year, there was the launch, and we were a bit nervous and excited. And there's our logo, a mission logo, on the capsule and the tip. We launched with a well-known American company, which really quite quickly managed to, within 9 months of negotiations until the launch. That was quite interesting. Rocket launches, everybody knows them, and this is the last picture we got from the outside, where Euclid was put into its journey to L2. What's L2? It's the Lagrange point 2, outside the Moon Earth system, 1.5 million miles away, kilometers away. It goes around the sun together with the Earth. There's always the same sunlight. We hardly move the telescope, and it rotates very slowly around the point, the L2 point. It's there. It's 1.5 million kilometers away from the sun. So. And it arrived there in August, and then we are starting now. What are we doing? 1/3 of the sky, I said. We look at the 1/3 of the skies. 14,000 square degrees, and we don't look at the Milky Way, that's too bright and there's too much dust. We don't look at the ecliptic, where that's the area, the plane of our solar system, and everything else is of interest. And we looked at the best 14,000 square degrees, and 6 years, for 6 years we'll be looking at that. We do something as simple as possible that always does the same thing and always creates the same temperature, because we need a really very stable temperature for the Viz camera. We took one spot, make 4 pictures, go to the next spot, take 4 pictures, and so on. Every 70 minutes a new field for 6 years. And this is really not an observatory like Hubble, but it's really an experiment. For example, like other experiments, it's quite inflexible, but does this one thing extremely well. So what goes on for 6 years? We do our sky survey. It has fuel about 4 more years, and we'll see what else we can do with that after those 6 years. And maybe there's a few years of data processing, and for the next years there's something that's going to happen. So we get data, very nice. We have a 35-meter radio telescopes. It's 1.5 million kilometers. It's the deep space antenna from the ESA. We get 4 hours per day, and we get the data with 75 megabits per second from L2. And we really need that because we need to transfer 100 gigabytes per day. And that's really quite something, but within 4 days per day, that is quite something, and they really had to extend the antennas that this was really working. And we have...
I will not say a lot about the data processing. We have data centers, 10 of them in Europe and 1 in the US. We have to see to really reach these goals of precision. So we had 10 years for the software, and there's a lot of work in there. And I have to say, it's running pretty well. And just wasn't like this with other missions. Yeah. And we are up there 10 months ago in southern France. Now it's at L2. And now we need some images to show a little stuff. Let's have a little paper, show some objects that may not be typical, not the thousands image of the same galaxy, some new stuff. So there are 5 or 6 projects, 5 already publicized images. There will be a scientific paper. Since like a month, I want to show them to you. What I want to say is, we have so many pixels that this is almost the whole picture of one of these fields. This is really a challenge to show this, because you cannot print this. This image has 25,000 times 25,000 pixels. This is a gigantic amount of detail that you can with a lot of telescopes, but with the same amount of details in the background and the size of the field. Euclid is pretty unique and has unique challenges. And I'll show you a link to ESA Sky, where you can zoom and drag around as much as you want. No, really. If you go there, that's the core of this Perseus galaxy cluster. What we saw a moment ago, this is the amount of galaxies, and if you count, there's like 1,000 galaxies in this galaxy cluster, but at the same time, in the background you see galaxies that are farther away. There are elliptical galaxies, these round and diffuse things, spiral galaxies, but all these small dots in the background that are not these shiny things that are stars in the foreground. The small stuff in the background, every point of that is a galaxy. If you take another area that looks kind of empty, you see These little small things, the crosses are stars. There's another galaxy cluster much farther away than this galaxy cluster. And behind it there are more galaxies. And in this one image there are 100,000 galaxies in the background. So from this one image you see 100,000 galaxies in the background. And next hour again, and so on. So we can show we have a lot of detail and a lot of stuff in the background. Details like, well, we can also look at the substructures of bigger galaxies. There's a lot in there. The second object that we looked at was the spiral galaxy. Very tricky. You can find it as a hobby astronomer, but it's partly you have to look through our Milky Way. But we had a pretty clear image with our near-infrared. So there's more galaxies in the background. We can take this little point here, so we can see, yeah, 5, 6 very bright stars. There's our Milky Way in the background, and behind that we see more stars, and behind that we see more galaxies. So we see galaxies through a galaxy that we see through our galaxy, and in the background there are more galaxies. The detail, the amount of detail is staggering. I could show this for hours. I could have, the guy who talked us through this, we could have listened to him for days, but well, we had to go on with work. That's a cluster, spherical cluster of stars that is quite close to us. What we can see is what a great definition we have. These are all singular stars in this cluster of stars, of 100,000 stars, that we can measure in detail. So you can do a lot of science that has nothing to do with cosmology, which is what most of the scientists do in our consortium. They don't want to do cosmology, they want to do all the other things. All this data goes to the world, it's publicized, everyone can look at the raw data, or at least at the reduced scientifically calibrated data. The last image, very atypical because we don't look at the Milky Way. We look at the Horsehead Nebula. This is a galaxy in Orion area. This Horsehead is an absorption of dust. And we see the light filter through it. And the cirrus, this blue stuff, gas and dust. If you look there, you can see a lot of cirrus, and you see through it galaxies. If you look into the largest cluster of dust and stars, you can see an almost three-dimensional image of the structure of stars. This is dust in our Milky Way. We can see a lot of detail, a large area at once. And now, and this is like looking forward. What will we look forward to in the next months and years? This will be the standard for this kind of data in the next 30 years. There will be no mission looking at this amount of area with that amount of clarity, because that's a lot of pressure, which is scary because it's a lot of pressure.
Yeah, in February we start with this 6-year sky survey. In February there will be maybe 10 additional poster and desktop background motifs will be published, and there's their first scientific papers. And in March of 2025 there will be the first mini data release, about 2,500 square degrees, and that's not a lot for us, but that's what Hubble did in its entire service life. A year later, then 25 times that much in 2026, and then after next year there will be the other results will come into the literature enter the literature, and it will be done a few years later. This is our website, the consortium, and the main ESA page for Euclid, and there's no malware behind these QR codes, but you can really use these. Right. So we'll see if there's time for some questions, maybe. So we have time for a few questions. We have 4 microphones in this room, and we also look at the internet, so Mastodon, IRC, Matrix, and so on. And usually a much smaller view than Euclid, but there are the first questions. If you, so really, we can start here. Hello, Knut. Thank you very much. One question: the data will be released in chunks over years. You just showed us. And what about this? Why do you do it like this and not in real time, open source? There is a concept first to have certain points where the data has a certain defined quality. We have raw data now, but they are not really usable for science, because if there's a brightness here and a brightness somewhere else, that doesn't mean the same thing. Especially for cosmology, what we do is we have a data release for cosmology, a big release. With this, you can certainly say whatever is measured in the ways of a form and shape, we can really release it as well, and we can really say what is the quality, what can it be used for, and what are the weak points. And these 5 square degrees are sort of a teaser, so the community really can hone their tools, and internally we can use that a little bit earlier, and that's the other way, the other side of the coin. Many institutes put a lot of resources in that, and that's really the payback for the institutes that were partners. They have a little head start, about 12 months head start for the data that they can use, and we are only a few people there, and a lot of projects won't be done with that. So we really have to come through the survey. We want to really have a certain data quality. And microphone number 1. Thank you very much for this research. It's very important, I think. My question is about one graph there, where it was about cosmic microwave background, the angular distances. And I noticed that with the lower distances, there were a smaller deviation and then became bigger, and then it became smaller again, the standard deviation. So what's that? Let me just take a look. It's this, going back through the slides. So I think this graph, yes, right. So you're talking about the uncertainties in the points or the lines? They're both, really. The lines, why are they diverging, and why is the lines, yes. The lines are really just models. What we could extract from the data, that's from the Sloan Digital Sky Survey from the ground. And I think the models correspond to different cosmological assumptions, but I think it's about the structural the forming of structures, where they have their peak, except the lowest one, they have the peak at the same distance, and they really show that this scale and this yardstick is always the same for all the methods, because I'm not really a cosmologist myself. So we have a few minutes, maybe some questions from the internet. Yes, there are some. At first, the Internet wants to know how big is the temperature difference between the cold and the hot side of Euclid. That's a good question. Euclid is not a lot further away from the Sun than the Earth, and the equilibrium temperature is about room temperature. So we really have we have warm electronics. That is about room temperature. It's about 20 or 25 degrees Celsius, and it's not especially cooled. The telescope is not actively cooled. On average, it really has only one temperature. So on one side, there's what you saw, the gold shimmer there is a real sun shield that should reflect the sunlight. And on the other side, we have radiators that radiate the heat from the instruments that need to be cooled. But the whole telescope, really the whole instrument, let's say the instrument area, there has only one temperature, and the differences are just tenths of millikelvins. It's in difference, really. Now, if we do a calibration measurement, if we have less than 100th of a degree over time doing the measurement, then it doesn't work, really. But overall, it has a very, very stable, very universal temperature. Only what is beyond the solar reflectors could have a slightly higher temperature, but I don't really know the number there. So I'm very sorry, but I'm very interested in the sky. But I can see that there are more questions, but of course you can really ask Knut and meet him afterwards. And thank you very much, Knut. And could we have another round of applause, please?